Okay, so for the given f, which takes an element from A and returns an element from B, decide whether f is onto and whether f is 1 to 1. So for our first example, we're going to look at A equals the ordered pair of integers, and B equals the set of all integers. So f is going to go from a coordinate pair to an integer. So here our f is going to be defined f of x comma y, where x and y are integers, equals x plus y, which is going to yield a single integer. So first, let's look and see if it's 1 to 1. I always like to start with 1 to 1. So our general tactic here is going to be taking the function and putting it in two different variables, setting them equal to each other, and then proving that those inputs are equal themselves. So suppose A, B, C, and D are elements of Z, so they're integers, and f of A, B equals f of C, D. So this is our assumption here. So we know, because these are ordered pairs, that if f of A, B equals f of C, D, then A equals C and B equals D. And that is if it's 1 to 1. A has to equal C and B has to equal D, because we know for a function to be 1 to 1, if it has the same outputs, so we're setting the outputs equal to each other, then they have to have the same inputs. Okay, so by definition of f, since f is of x, y equals x plus y, f of a, b is going to equal a plus b, and f of c, d is going to equal c plus d. So we have, by definition of f, a plus b equals c plus d. Now, we know that addition in integers is commutative. So a plus d plus b equals c plus d does not necessarily mean a and c and b and d are equal, like when we looked at an ordered pair. So let us take ab to equal the ordered pair 2, 4, and cd to equal the ordered pair 4, 2. Now these are not equal. This is the ordered pair 2, 4, and this is the ordered pair 4, 2. So 2 plus 4, if we bring this equality down, equals 4 plus 2. And that this is true. This equals 6. But since AB doesn't equal CD, our inputs are not equal, but we got the same output of 6, we know F is not injective, or F is not 1 to 1. F is not 1 to 1. Okay, so now let's look at and see if F is onto. So the way you're going to find if something is onto is you're going to want to pick an arbitrary element in our codomain. So we're going to pick something arbitrary that will be an output and show that something in our domain maps to it. Okay, so here let's let an arbitrary element B be an element of C. So B is an output and it's an integer. So F, now remember what our F is. F of x, y equals x plus y. So your inputs are added together. So here we want to show that something maps to B. So what adds together with B to get B? 0. So f of B, 0. 0 is an integer, so that works here because our inputs are integers. And B, we already said, is an integer. So this is going to equal B plus 0, which equals B. So we picked an arbitrary element in our codomain and showed that this ordered pair in our domain mapped to it. So we can conclude that F is surjective, or onto. Okay, so let's pick another example. So this will be B. Let A be in a set of all integers and B be an ordered pair of integers. So it's kind of the opposite of our last problem. We're going to take an integer and the output is going to be an ordered pair. So here our f is going to be defined, f of x equals x comma 1. So x is going to be all the integers. So this is going to look like 1, 1, 2, 1, 3, 1, and so on. And then it can also go in the negative direction. So first, we're going to see if it is 1-to-1. So remember, our tactic here is going to be, let's let A and B be elements of Z such that f of A equals f of B. Because we always want to set the outputs equal to each other, because then we can prove that our inputs are equal if the function is 1-to-1. If they are not equal, then it's not 1-to-1, because for you to have the same output, you have to have the same input for it to be 1-to-1. So by definition of f here, here's the definition. We have A comma 1 equals B comma 1. And since in ordered pairs, the corresponding coordinates are equal to each other, so 1 equals 1 and A equals B. So this implies A equals B. Thus, F is 1-to-1. Okay, now let's decide if F is onto. So this was 1-to-1. Now let's decide if it's onto. So we know our f is f of x equals x comma 1. So let's pick an arbitrary, we can kind of see that this isn't going to cover all integers because this second coordinate is a set integer, it's 1. So this second coordinate is not going to cover all integers. So we can just pick anything. We know that we can kind of look at this and know it's not onto. So let's pick something. Let's say since 1 comma 2 is an element of the ordered pair of integers, and there does not exist an x in Z such that x comma 1 equals 1 comma 2, f is not onto. So we knew that 1, 2 was an element of an ordered pair, and we knew that since the second coordinate is fixed to 1, 2 will never be covered by this mapping. So f could not be onto. Okay.